let me show you two problems that you'll see in the context of optimization. Imagine you are a farmer and your mission is to build a rectangular farm. Now, you have 100 meters of fence. Now, naturally as a farmer, you want to maximize the area available to you with your 100 meters of fence. The question becomes, what are the dimensions of your farm to maximize the area with 100 meters of fence? Now, it's kind of an interesting question because we know that the area of this farm is going to change, where the rectangle will always have a perimeter of 100 meters. And no matter how you lay out the rectangle, the area will change. And so there has to be some combination of dimensions that optimizes the area, or where the area is a maximum. We're going to visualize a second problem. Now, let's imagine you are designing a cross section of a skip bin, and your company requires you to have the cross section in the shape of a trapezium, where they say, okay, you're going to have a base of 2 meters, and the two reinforcing pieces of metal that are going to structure this trapezium are also 2 meters long. The question becomes, well, you want to maximize the cross-sectional area of this skip bin, so you wish to maximize the area of this trapezium. Now, although both of these problems, under the context of optimizational calculus, we're going to have to take a problem-solving approach to this. Now, up on the screen here, I have got my guide to solving optimizational problems. I would recommend draw a large diagram with the given information. That'll be the very first thing I do. After that, I want to identify what I'm trying to maximize or minimize, or I really should change this word to optimize. All right, I want to identify what I'm trying to optimize, and I'm going to use my understanding of relationships to construct equations, because I need to lead into step 3 from here is I need to get all of my information in terms of one variable, because when I've got things in terms of one variable, this is written as a function. I can take the derivative of a function, I can find the maximum of a function, I can determine the nature of stationary points of functions, so I can do all of this calculus stuff. And since contextual problems involve a domain, we are going to be considering the global max. So when we find our maximum points, we also need to look at the end points of our domain. Let's plug through this first problem here. So it says determine the maximum area of a rectangular field that can be enclosed by 100 meters of fencing. Show full working of a calculus. So first thing I'm going to do is draw a nice diagram. So I've got my rectangular field there, and then now, if I look back at step number 2, I'm going to identify what I'm trying to optimize here. That would be the area. So I'm maximizing my area, and I know that the area is equal to length times width. And what I've also been given here is I've got 100 meters of fencing. Now, the fence implies what I am enclosing all of this stuff with, and that is the perimeter of my rectangle. So I would say the perimeter is equal to 100 meters. And how I calculate the perimeter is it's equal to 2 outside of length plus width. So from here, I can actually formulate some equations. I've got the perimeter, it's fixed at 100 meters. So if I say I've got 100 is equal to... What I need to do here is I have done step number 1. I've drawn a diagram. Step number 2, I'm using my understanding of relationships. That's knowing what the area formula is, knowing what the perimeter formula is. I've constructed equations from my information. Step 3, I need to get all of this stuff in one variable. Now, I am trying to maximize the area. So I want to have the area as a function of one variable. At the moment, the area is a product of length and width. That's 2 variables. Let me see if I can do a bit of substitution here with my constraint. All right, so what I find out is very nice. I just rearrange the equation. I get L as the subject, get it by itself, and I do this so I can plug this guy, this L, right back into here. And when I do that, I'm going to have the area. So I get the area is equal to 50w minus w squared. Now I've written it in this function notation because what we have got here is actually really important to actually understand what we've got here. what this relationship here is telling me is that the area is determined by width. So that means if you tell me what the width is, I'll be able to tell you what the area is. And if you want to think of it as a graph, you've got area is your y-axis and width is your x-axis. And you'll notice that is just a parabola. It's 50w minus w squared. That is a parabolic relationship. It's kind of going to look something like that. And so what our task is to do is to find the maximum area. So that would be finding our stationary point, setting it equal to 0, which is exactly what step number 4 in this process tells us to do. It says take the derivative of the function, set it equal to 0. That's because we want to find the stationary point, determine the nature. So we've got a maximum or a minimum or a point of inflection. So we'll go ahead and do that. So we get, well then, therefore the width, to find the maximum area, the width would have to be 25 meters, which then implies that, well, the dimensions of my rectangle, if the width is 25 meters, that also then means that the length is equal to 50 minus w, which is 50 minus 25, which is 25. So that means I get the length to be 25 meters, the width to be 25 meters, and I can determine what the area would be. It would be length times width, which is 25 meters, times by 25 meters. And as we visualize there, 625 meters squared. Very nice. So now if we have a look at this second example here, we get a cross-section of a skip bin is to be an isosceles trapezium. Really what that is saying is it's got to be a symmetrical trapezium about both sides with 3 side lengths of 2 meters, as we can see in the diagram. Determine the angle that maximizes the cross-sectional area and calculate this maximum area. Draw a big diagram. Well, it's already done for us, which is very nice. Now I need to construct some equations and identify what I'm trying to maximize or minimize or optimize. I'm asked to maximize the area. So I note that the area of a trapezium, this you're just going to have to know, is h outside of b plus a over 2, where a is your base, b is your top, or other way around, doesn't really matter, and the height is from top to bottom, perpendicular height, top to bottom there. And so if we can imagine at this point, as this angle changes, the area of the trapezium must also change. All right, they are corresponding, and there's got to be a level of symmetry here. So if we've got this angle there, both of those sides of the trapezium have got to increase or decrease by the same angle. Otherwise, the shape is not a trapezium, right? That would be a misconception of this question. So what we are trying to get at here is we need to determine h, b, and a with one variable, because at the moment we've got area is dependent on height, base, and top, a. H, B, and a. That is not helpful. I need to get all of this information in one variable, because when I've got stuff in one variable, I can do calculus. What I'm going to write out here is what h is equal to, what a is equal to, and what b is equal to. We'll start with the easiest one, which is a. It is just 2 meters, right? That's that bottom one here, which is very nice. Now h is going to be, if we look at this diagram, I would say that this length would also be h. Okay, that length would also be h. The hypotenuse here is a length of 2 meters, and I've got some angle in there. Now, I can relate all of these variables by trigonometric ratios. So where I'd say this is my opposite, this is my hypotenuse, which would be very nice, because then I can say that, I would do it in a green over here. Actually, I might do it in a green, no, I'll do it in a green over here. That means that sine of theta is equal to h divided by 2. Right? That's just using sine equals opposite over hypotenuse. I can rearrange this for h. I would say that 2 times by sine of theta is equal to h. And that's what I'm going to plug in here. So instead of writing h, I know that's equal to 2 sine of theta. Now, what we're going to also notice here is because this has got to be symmetrical about both points, that's a h there, we are going to have the same distance from here and here. I'm going to call that x. So x. And we would say that b would be equal to 2 meters plus 2x. That's the whole top distance. 2 meters plus those 2x's there. Then we've got another problem. Well, what is x? Because we've just introduced another variable. But we can actually relate this with our angle. Because if we use some symmetry here, this down here would also be x. Using this angle here, that is my adjacent. Again, I've got a hypotenuse of 2. I can relate this by cosine and say that is x over 2. And I can rearrange this and say 2 times cos of theta is equal to x. And if I plug this back in for my b expression, I get b is equal to 2 meters plus 2 outside of x, which is 2 cos of x. 2 cos of theta. And if I simplify this a little bit more, I get 2 plus 4 cos of theta. And if I plug all of this back into, so if I plug in my a, h, and b back into my area, what I'm going to get is the area with respect to the angle, which is absolutely crucial because what I'm going to have is the area with respect to one variable. That way I can apply calculus, find maximums, find optimal answers. So good, so good. All right, we get a area function with respect to the angle. Now, this is, I don't want to understate the importance of this. This is telling us that if you tell me what this angle here is, I will give you the area of the trapezium. If you tell me what that angle is, I will give you the area. That's what we have found out here. Okay, now it is also important to note here that we've got a domain on theta, so I would actually make a note and say that theta is going to be stuck between 0 and a pi on 2. All right, it's stuck between 0 and 90 degrees. Okay, because it can only rotate from that right angle there. That's how the trapezium is going to be manipulated. Now we're at the stage we have got everything in terms of one variable. I need to find the optimal area. So I'm going to take a derivative, set it equal to 0, and verify that it is a maximum. Okay, so we simplify our expression here. I'm going to let the derivative equal 0 to find or to optimize. And so we're at a, well, look, we're in a bit of a pickle here because we don't really know how to solve this at the moment. But what we can do is we can spot that sine squared is equal to a 1 minus cos squared. And this is the Pythagorean identity where we say that sine squared plus cos squared equals 1. And so we can rearrange that and we can say, well, sine squared is actually equal to 1 minus cos squared. When I make this substitution, I'm going to actually be able to solve this because I can factorize. Now, look, I probably could have done this earlier by just dividing by 4 to simplify it. Probably should have, but I can just divide by 4 now, and I get 2 cos squared theta plus cos of theta minus 1. And so I can actually factorize this. What I might actually do is I will let k equal cos of theta. So a bit of substitution here because this actually just becomes a quadratic where you say 0 is equal to 2k squared plus k minus 1. Now I need to factorize this. What I can do is I can say I've got 2k squared plus 2k minus k, because 2k minus k is just k minus 1. That way I can pull out a common factor here of the first two terms. I can pull out a 2k. I get k plus 1. And the second term, I can pull out a minus 1 there, and I get a k plus 1 come out. So then what I've got here is I've got 2k minus 1 and then k plus 1. That is factorized. By the null factor law, you would say that 2k minus 1 equals 0, or k, well I should say and k plus 1 equals 0. That implies that k is equal to negative 1, and then here we'd have k equals a half. Resubstituting this back, what this means is we've got a half equals cos of theta, and we've got negative 1 equals cos of theta. Now we can do something with this because we can utilize the unit circle. And what we get here is something we can actually pull out. So we can get, well, what we've got here is, well, cos of theta being equal to negative 1, the solution for that theta would actually be a pi. Now, that's outside of our domain. We're only considering between 0 and pi on 2, so we would reject, we're going to reject that. Right? Okay, since it's reject out of domain. What we've actually got here is another 2. We are interested in cos of theta being equal to a half. Cos of theta is an adjacent over hypotenuse, so my angle is going to be pi on 3. This implies that theta is equal to pi on 3. Draw that in my unit circle out here, pi on 3 there. Everything is positive there. Cos would also be positive here. That'd be 5 pi on 3 out there. And I'm not even going to consider that other solution because it's outside of the domain. So really the only theta value I've got that I can pull out is theta is equal to pi on 3. That is my maximum, right? Now I need to verify that this is a maximum, so I will use the first derivative test. So I know at pi on 3, I've got a flat slope. I'm going to pick two nice points, which is 0 and pi on 2. So I would say that the slope, what's it doing between these points? So I'm going to consider it when it's 0. So therefore, we'd have to conclude that, well, pi on 3 is actually maximum because the slope area is increasing, then it's flat, and it's decreasing. So I'd say therefore, theta equals pi on 3 provides a maximum area. Now what that area actually is we'll just plug it into our area function. Where is it? Right up the top. We'll just plug it right into here to figure out what the area is. So I'd say A of pi on 3 is equal to sine of pi on 3, 4 plus 4 cos pi on 3. Again, unit circle it out, sine there, cos there. No, you know what? Forget the unit circle. Let's just draw up our pi on 6, pi on 3, that's a half there, that's root 3 on 2 there, that's 1. So if I'm considering sine of this angle here, I'm going to have the opposite over the adjacent. So I'm going to have root 3 on 2 there, multiplied by 4 plus 4, and then I'm going to have adjacent over hypotenuse, that is a half. Simplify this out, I get root 3 on 2 times by 4 plus 2, so that's going to be 6. So it's equal to 3 root 3 units squared. That would be my area.